Hi, my name is Michael, and I'm going to be talking today about Junta distance approximation with sub-exponential queries. This is joint work with Vishnu Iyer and Avishai Tal. So first, let me introduce the general setting, which is property testing. This was first introduced by Bloom, Luby, and Rubenfeld, and subsequently been explored by many people. So the idea is that you have query access to your function to some function f, and for us, we're going to be dealing with Boolean functions, and we're going to represent bits by plus or minus 1. So we're going to be dealing with Boolean functions that take in bits to just 1 bit. And you want to distinguish between whether the case when f has some property, pi, or f is epsilon far from having some property. And so there's a couple things to talk about here. First, by query access, we mean that I have access to some black box, and I can give this black box an input x, which is just n plus or minus 1s, and the black box will tell me what the value f of x is. Just spit it back out to me. I don't want to use this box. It's expensive to use this box. I want to use it as little as possible, but I have access to it. Another thing to mention is that what we mean by far. So our notion of distance throughout this talk will be that of relative Hamming distance, which just means I'll say that f and g are epsilon far if they differ on an epsilon fraction of their inputs, of which there are 2 to the n, since they're both Boolean functions. So in particular, we're going to be looking at Junta testing. We'll say that f is a k Junta if it only depends on k of its inputs. More precisely, if you can write it as g, another function g, which is just a function of k of the inputs. So this is motivated by the fact that many interesting function classes are just subclasses of k Juntas. For example, like S-term DNFs or CNFs, or small formulas, or small branching programs. Many of these are just small formulas, for example. Many of these are just subclasses of the K-Junta class, and very well studied throughout theoretical computer science. Another natural motivation comes from machine learning. You might have data with many inputs, and running a learning algorithm is expensive, but so maybe you first want to test whether or not your data, whether or not you actually are dependent on all of the inputs. If you're close to depending on only a few of them, then you can run your Junta learning algorithm, which is more expensive. But other motivations come from probabilistic checkable proofs, dictatorship testing, and long code testing, which I don't have time to get into. So in particular, this is just applying the definition from the previous slide. We want to be able to distinguish the yes case when f is a k Junta, and the no case when f is epsilon far from every k Junta. So this was introduced, or first studied really by Fisher et al., this problem of k Junta testing in particular, and it's been further studied by many people. And the long story short is that we have tight upper and lower bounds for this problem. Blay showed that any k Junta can be tested with just k log k queries to f. And recently, Soglum showed that this is actually necessary. You need k log k queries to test any k Junta. And another important thing that I'll point out here is that the number of queries is independent of n, which is the ambient dimension. Remember, f is a function from n bits to 1 bit, and we're trying to test whether or not it's a k Junta. And we don't have to, so n could be astronomically large, and k could be some constant. And what this result tells us is that we can test whether or not f is a k Junta with a constant number of queries if k is constant. So what we'll be focusing on today is actually a slightly generalized notion of property testing known as tolerant property testing, So in this case, the only difference is that now the yes case is not f is in pi or has the property, but instead it is epsilon prime close to pi, meaning there exists some g such that the distance, that g that has the property and the distance of f and g is at most epsilon prime. So we're trying to distinguish between the green and the red region. And again, we have this region of slack where we're allowed to answer anything or be incorrect in general. And as epsilon and prime and epsilon get closer and closer together, the problem becomes more and more difficult. So this problem has been studied. First, Blay et al. Gave a tester that makes exponential and k mini queries and distinguishes between the yes case when f is epsilon over 16 close to some k junta, and a no case when f is epsilon far from any k junta. So, and then subsequently, soon thereafter, Deimos and Niemann gave a tester that makes exponential and k mini queries and polynomial 1 over epsilon, and distinguishes when f is c minus epsilon close to some k junta, and the no case when f is c far from any k junta. So the things I'll point out here is that there's a multiplicative gap in the Blay et al. Result. So even though they have a slightly better dependence on epsilon, this multiplicative gap precludes one, for example, from setting epsilon to be 0.15 and epsilon prime to be 0.1, which the Deimos and Niemann result allows one to do. In terms of lower bounds, Levy and Weingarten showed that any non-adaptive tolerant testing algorithm requires at least k-squared queries. So this is interesting because it shows that tolerant testing of k-juntas is strictly more difficult than the standard testing of k-juntas, which you can do in k-log k queries. Or more accurately, k to the 3 over 2 queries for non-adaptive algorithms. More recently, Palavor, Rasodnikova, and Weingarten showed that non-adaptive testers require at least exponential in nearly square root k queries to distinguish between f that is 1 over k to the 0.51 close to some k junta and f that is 1 over square root k far from any k junta. So this is a much stronger lower bound, but on the other hand, epsilon and epsilon prime are not constants as they were in the result of Levy and Weingarten. So now we're ready to state our main result now that we have some context. We give a tester that makes exponential in O tilde of square root k over epsilon queries and distinguishes between the case when f is c minus epsilon close to some k junta and the no case when f is c far from any k junta. More precisely, we just return an alpha that is approximately the best correlation f has with any k junta up to some additive error of epsilon. It's an easy corollary once you see, like, once you have this distance approximation result, you can easily get out this tester that we claim. So I'm going to talk about our techniques to achieve this, but first, in order to do that, we need to talk about some background in the Fourier analysis of Boolean functions. So a very standard fact by now is that any Boolean function can be expanded as a multilinear polynomial in the Fourier basis, where you can write it as some monomial and a coefficient to that monomial. It's called the Fourier coefficient, f hat of s. And so, for example, the maximum of two variables can be written as a multilinear polynomial in this way. And you can check that it works on all 4 possible inputs. But the really useful and nice thing is that it doesn't just work for the maximum of two variables, it really works for any Boolean function, which is very useful. So a few properties of this Fourier expansion that are standard, but we'll go through them. First of all, the sum of the squares of the Fourier coefficients is equal to the expectation of f squared. This is just is called Parseval's identity and comes due to the fact that the Fourier basis is an orthonormal basis. But importantly for us, f is plus minus 1 valued, so the expectation of f squared is 1. This tells us that the sum of the squares of the Fourier coefficients equals 1. And in particular, you can think about the Fourier coefficients, the squares of the Fourier coefficients, as defining some sort of probability distribution over the subsets of n. And indeed, because they're all positive and they sum to 1. And so, in addition, we have this nice expression for the variance in terms of the Fourier coefficients. And this brings us to one of the most important notions in all of the analysis of Boolean functions, which is the influence of a coordinate I, inf I of f. This is equal to the probability that the function changes value when you flip the ith bit. And it turns out it has a very nice Fourier representation. It's simply the sum of the squares of the Fourier coefficients containing I. This means that the total influence, I of f, which is just the sum over the individual influences, also has a nice Fourier representation, which is the sum of all the Fourier coefficients squared, scaled by the size of the set S. In particular, we're going to also, in the talk coming up, we're going to have to be dealing with what is known as the annotated or the truncated influence up to level k. This is just the sum of the square of the sets containing I, their Fourier coefficient squared, as long as the set is less than or equal to k. So one useful property of this is that if you sum over all these truncated influences, it's at most k, or more accurately, at most k times the variance of f. And we'll use this later. So now we can talk about our tools. One of our main tools, perhaps our main tool, comes from the work of Day, Mossel, and Niemann, and it's a notion of coordinate oracles. So a coordinate oracle is really just a dictator function. You give it x and it outputs x sub I. This is not so interesting or difficult to do by itself if you can look at all of x, but remember we're trying to keep the query complexity independent of n. So this is where the subtlety comes into play. Stated in general terms, the result of Day, Mossel, and Niemann is that they give a polynomial in k over epsilon query procedure that produces approximate coordinate oracles to a set of roughly k squared important coordinates to f. And so this is hard to parse at first. I'll say a couple things. The high-level idea is that S contains, so if G is the closest k Junta to F, it depends on some k coordinates, say we'll call the set T. The idea that we would like to be true is that T is within S. Somehow we are able to get oracle access to the coordinates that G depends on, which G is the closest k Junta to F. If that's the case, then we only have to worry about finding the best k Junta within S. And so we've effectively reduced the dimension of our problem from n down to roughly k squared. This is indeed how Day, Mossel, and Niemann achieve their result and get a query complexity that is independent of n. Okay? And the reason the diagrams above are drawn the way they are is because each of these coordinate oracles works by querying f some number of times and then outputting what it thinks x sub I sub j is. Okay, so now let's talk about what S actually is. S is going to be a set of coordinates that have large low degree influence. So we're only looking at the influence below level k because we're concerned with k juntas. And we're going to specifically look at coordinates whose influence is at least epsilon squared over k. Truncated influence, that is. And so a simple claim, which I'm not going to prove, but you can find in our paper, is that if G is a k junta that maximizes the correlation, so it's the closest k junta to F, and if T is the set of coordinates on which G is supported, then there's some junta G prime on whose support is on T intersection with S, such that you only lose an additive error of epsilon in the correlation with F. So what this is really saying is it's really just justifying our idea that we can just restrict ourselves to looking at only the coordinates in S. Because if we do that, we're only going to lose at most an epsilon additive error in the correlation with the nearest k junta. Another note is that the size of S is at most k squared over epsilon squared. And this just falls out of the fact that the sum of the truncated influences is at most k, which we saw a couple slides ago. So the theorem, which we mentioned before, which hopefully should be starting to make a bit more sense, is that there exists a polynomial in k over epsilon query algorithm that yields coordinate oracles such that every coordinate in S has an oracle. And it doesn't output too many extraneous oracles as well. And so now we've effectively reduced ourselves down to looking at only k squared inputs. Crucially, we don't know what these inputs are. We just have access to them via the oracles. But it would take log n bits to even specify one of F's inputs. So it's a subtle notion. So our main motivating question was, can we take this like set S and reduce it down to something that's just O of k? Maybe O of k over epsilon, but I'm treating k as the more important parameter here. The main bottleneck is the fact that the sum of the truncated influences is at most k, which is nice, but it's not nice enough for our purposes. We were pondering how to come up with a notion of importance of a variable, but have this importance not have too large of a sum. And after some trial and error, we came up with this notion that we called the normalized influence, which is extremely similar to the influence, but now you look at the sum of the squares of the Fourier coefficients containing I, and you normalize them by the size of the set itself. So intuitively, this gives more weight to Fourier mass that comes from the lower levels. And this was also initially considered by a work of Talleyrand in the 90s, but we didn't know that at the time. So a couple claims about this normalized influence. First, if you sum over all the normalized influences of a function, you just get the variance of f, which is super nice for us because f, remember, in our setting is Boolean valued, so the variance of f is at most 1. So that's very nice. And the proof is just a simple one-liner. The reason the equality in the center is true is we are overcounting each f hat of s squared term exactly the size of s many times. And so this 1 over size of s times size of s cancels out very nicely, and you just get the variance of f. Another even more important thing for us is that if we look at the closest k junta to f and say it has some constant correlation c, then the sum of the normalized influences within T, which is what G is supported on, is at least c squared, minus the empty Fourier coefficient. But ignoring the empty Fourier coefficient and treating c as a constant, this is very nice for us, as we're about to see. So the proof again is a very simple one-liner, and it's almost the exact same logic as the previous proof, so I won't dwell on it too much. One of our main technical lemmas, though, is that this normalized influence can be estimated up to a multiplicative factor of 4 in a polynomial in L many queries. Okay, so here's how we're going to reduce the number of coordinates we have to consider. We're going to estimate all of the normalized influences for all of the coordinates we have oracles to, and we'll sample coordinate I according to its normalized influence. And by what we saw in the previous slide, and by the fact that the sum of the normalized influences is at most 1, if G is a K-Junta, then if G is the K-Junta that is closest to F, and it has some constant correlation, then the probability that we sample a coordinate from T is at least c squared, which is, again, just we'll think about as some constant, which is super nice, because we can just repeat the sampling procedure, O of K times, and there's some details to deal with in terms of, making sure we'll randomly restrict the variables that we already queried so that we don't query them, or sampled so we don't sample them again. But the high level is clear. We just repeat the sampling procedure O of K times, and either we will have seen all of T, we'll sample every coordinate inside T, or we'll sample every coordinate within some T prime. And this T prime basically represents a cover of T. We show that there exists a function G prime on T prime that G lose a additive correlation at most epsilon. So overall, this gives us an algorithm that makes polynomial in K over epsilon queries and gives us implicit access to O of K queries, called S prime, such that the best correlation of F with a K-Junta is approximately equal to the best correlation of F with a K-Junta whose coordinates are only in S prime. Now, it turns out we can estimate the best correlation of a junta on S prime, so an O of K over epsilon squared junta and F. So this leads to the following corollary. With polynomial mini queries in K, we can distinguish between F that is C close to being a K junta and C plus epsilon far from being an O of K over epsilon squared junta. So in terms of practicality, this algorithm is much more practical because it's polynomial query in time, but it's not our advertised main result. But for reference and comparison, there have been similar results of this type. Blay et al. In the same paper gave a tester that made polynomial in K over epsilon queries and distinguished between F that is close, epsilon over 16 close to some K junta, and F being epsilon far from any 4K junta. So their result is better in the sense that they have 4K instead of O of K over epsilon squared, but it still has this multiplicative gap that precludes one from certain values of epsilon and epsilon prime. Day, Musel, and Neiman gave a similar result. The only difference between theirs and ours is that they had O of K squared, which, that was the work we've done in the last several slides, was reducing K squared down to K. Okay, so now we're arriving at our main result, which is the sub-exponential query algorithm. And it's going to look remarkably similar to what we've already seen. So, which is why we talked about the previous algorithm first. The previous algorithm sampled just one coordinate at a time. Each sample was in t with some constant probability. The chance that all k samples fell in t, if we did this, was exponentially small in k. So immediately, this does give a exponential query algorithm. We could just repeat the previous algorithm exponentially many times in k, and with good probability, at least one of the times will work. One of the times will have sampled all of t exactly, or a nice cover of t. But this isn't so interesting because, well, two results already had exponential and k query algorithms. So we wanted to do better, or we wanted to see if we could do better. And our deal was to sample more than one coordinate at a time. To do so, we're going to introduce the definition or the idea of a normalized influence of a set rather than a single coordinate. Normalized influence of the set looks very similar, just the normalization factor is a bit different. And the idea, it will be exactly the same. So before we were sampling coordinates according to their normalized influence. Now we're going to sample sets according to their normalized influence. So a couple of facts which are very similar to what we've already seen with the normalized influence of coordinates. If you sum over all the normalized influences of sets of a certain size, this is at most 1. It's indeed equal to the sum of the Fourier coefficients squared above a certain level, u. And if you sum over the normalized influences of sets of a certain size within T, which we're thinking of our special set, this is exactly equal to, or at least equal to the sum of the Fourier coefficients within T of at least size u, or for sets at least size u. And again, we have the same lemma where we can estimate the normalized influences in poly L queries. L for us is k squared, so this is poly k. And our algorithm is going to be exactly the same. We're going to estimate the normalized influences, and we chose to estimate them for all sets of size square root k. This choice will hopefully become clear shortly. And then we're going to sample according to this normalized influence. So first thing I'll note is that estimating all of these normalized influences takes roughly 2 to the square root k time in queries. Really, it's k to the square root k. K choose square root k. But that's, works out to 2 to the O tilde square root k. And the other thing is that if the sum of the Fourier coefficients within T above level k is large, say epsilon squared, then we're going to sample a subset U of T with probability epsilon squared. So if we're thinking of epsilon squared as a constant, this is very nice. With constant probability, we're going to get square root k brand new coordinates of T. Whereas before, we were only getting one at a time. Okay, so this is a lot of math going on. Let's just think about this pictorially. We have like k squared inputs in total, and we want to sample some subset of k of them, T. And we're just sampling one at a time, square root k, and with decent probability, we're getting subsets that fall within T. Certainly not all of them do, but this is the idea. And so the idea is that we're going to keep sampling sets of size roughly square root k until the Fourier mass on sets above level square root k is small. Once it becomes small, how do we finish the argument? So once it becomes less than epsilon squared, how do we finish the argument? Well, it's actually quite simple. It's basically just triangle inequality. The first equality you're going to have to take my word for. It turns out that the correlation or the best correlation of f and g within T is this expression, the absolute value, the sum of the Fourier coefficients. Simple to prove. You can find it in our paper if you're curious, but take my word for that, and we can just apply triangle inequality and split on the sets that are of size less than or equal to k, square root k, and size that are sets of size greater than square root k. And then this is just plus, so this results in an additive error of at most epsilon, which is again what we're looking for. And so once we're down to this, so once we only have to consider the Fourier coefficients below level square root k, this is very nice because we can estimate all of these Fourier coefficients. Because there's only like roughly k choose square root k of them, which is roughly 2 to the O tilde of square root k. So we can just estimate all of them. This takes exponential and square root k many queries. And then we have to iterate over all potential sets T, because we don't actually know what T is. It's just like a tool of our analysis. And we calculate this correlation. And so this is the part of our algorithm which is perhaps not as ideal, is that this takes exponential and k time. But as I said, there's only exponential and square root k many Fourier coefficients to estimate. So that's like phase 2 of our algorithm. And both phases take roughly 2 to the square root k queries. But the second phase takes exponential time. So to recap, our main result is that we give a tester that makes sub-exponential, exponential, and square root k many queries. And we are giving an additive epsilon error estimate to the correlation with the nearest k-length. And just to mention a few open problems. First, our running time, as we mentioned, is exponential in k. So a natural question is it possible to tolerantly test k-juntas in less than that amount of time? We think it's not possible, but we don't know. Another natural question to ask is the power of adaptivity in the context of k-junta tolerant testing. So our adaptive upper bound looks similar to the non-adaptive lower bound that we saw a few slides ago. And so there's two obvious questions here. Is one, can we prove a similar lower bound, some better than polynomial? Currently, there's no adaptive lower bound for tolerant testing of k-juntas. So can we prove a similar lower bound for adaptive testers? And the second question is, can we remove additivity from our tester, which our tester uses additivity in several places, so this is not immediately obvious. Lastly, one might hope that quantum property testers can do better. So quantum property testers can query in superposition. And in particular, they can query according, or they can sample according to the Fourier distribution of f very easily. This seems to be useful, but it's not immediately obviously how this is useful when f has a lot of Fourier mass coming from lower levels or from sets of small size. Okay, thank you.